Okay, so lecture 60, chapter 6. Let's just start that all over. Chapter 6 is on the qualities of transient response, and we're going to be especially focused in this chapter on what happens during that initial period when the initial conditions are still dominating the response, or are still a significant factor in the response. Remember, after the transient period, we come to some steady state, assuming that the system is stable. Otherwise, it just blows up to infinity, and there is no steady state. So we want to really characterize that first portion of the response. And we're going to do that in this chapter by looking closely at first and second order systems, not just because they're easier. I mean, they are easier to analyze. So like linear first and second order systems are some of the easiest ones analytically to deal with. And in some ways, we deal with them because they're easier. We don't deal with nonlinear ones, for instance, time-varying ones first, for instance, or higher-order systems first, for instance, because first and second-order systems are easier. However, it doesn't mean that it's unimportant to look at first and second-order systems, because fortunately, higher-order system responses are just sums, can be thought of as being composed of sums of first and second order responses. Okay, so we'll explore this a little bit more later, but for linear systems at least, you're going to see all the same characteristics for responses to higher order systems, responses of higher order systems. You're just going to see the first and second order responses just summed together in those higher order responses. So it's a very useful thing to learn very thoroughly is how first and second order systems respond, because higher order systems will also respond like that. Usually there will be some dominant pole, we'll call it, or dominant root of the characteristic equation. And we already saw the dominant time constant, which is what that root of the characteristic equation is for the first order system, and something similar can be said for second order systems and higher order systems as well. So yeah, that was kind of the idea. And also everything looks like a first or a second order system can be like something that you can use. It's not universally true, but I would say it's really most things look like a first or a second order system, even if they're higher order or maybe a little bit nonlinear. Not everything really, though. It's just sort of an approximation, that phrase. So in this chapter, we primarily consider systems represented by single input, single output ODEs. We have the familiar notation: Y is the output, U is the input, T is time, F is a forcing function, constant coefficients A and B, N is the order of the system, it's an integer, M is less than or equal to N, and it's also an integer. And we have the differential equation in 6.1a, which has the time derivatives of the output, Y, on the left-hand side, different derivatives of Y and also scalings thereof, summed together. And the right-hand side is the forcing function F, which is described on the next line as being the sum of a bunch of derivatives of the input. Okay? So note that the forcing function F is related to but distinct from the input U. This is an important difference in terminology. So the input is there. The forcing function is the sum of all of these terms that depend on the input. We have to be pretty precise with our terminology here, otherwise it causes a ton of confusion. So we'll try to be very strict about calling something that enters in to the equation as u, the input, and something that is the right-hand side, the entire right-hand side of the differential equation, the forcing function. Okay. Good. So that's all. So any questions so far? We're going to start out with first-order systems.